If you've ever watched a science fiction movie and wondered whether time travel could actually be real, you're not alone. Time travel has captivated human imagination for centuries, from ancient myths to modern blockbusters. But here's what might surprise you. Time travel isn't just fantasy. It's a legitimate subject of scientific inquiry, studied by physicists at the world's leading universities and research institutions. So, what exactly is time travel? At its core, time travel means moving between different points in time, just as we move between different points in space. We're all time travelers in one sense. We're constantly moving forward, through time at a rate of 1 second per second. But when physicists talk about time travel, they mean something more dramatic. The ability to jump forward into the future faster than normal, or even more incredibly, to journey backward into the past. The scientific foundation for time travel began in 1905, when Albert Einstein published his theory of special relativity. Einstein showed that time isn't absolute. It flows at different rates depending on how fast you're moving. This wasn't just theoretical speculation. We've proven it with atomic clocks on airplanes and satellites. Time actually passes more slowly when you're moving at high speeds. This is called time dilation, and it's your ticket to the future. 10 years later, Einstein's general relativity took things even further. He revealed that massive objects like planets and stars actually bend the fabric of space and time itself. This opened up wild possibilities: wormholes, black holes that warp time, and even solutions to Einstein's equations that allow loops backward through time. Throughout the 20th century, brilliant physicists discovered various theoretical pathways for time travel. Some require rotating black holes. Others need cosmic strings left over from the birth of the universe. A few demand exotic matter with negative energy. All of them push the boundaries of known physics. In this video, we'll explore 17 different time travel theories. Some are grounded in well-established physics, like general relativity. Others venture into cutting-edge quantum mechanics or speculative territory. We'll cover everything from the scientifically robust, like time dilation near light speed, to the highly theoretical, like tachyons that might travel backward through time. Why do scientists take time travel seriously? Because the mathematics works. Einstein's equations don't forbid time travel. They actually predict it under certain extreme conditions. Whether those conditions can exist in our universe is another question entirely, and that's what makes this field so fascinating. By the end of this journey, you'll understand how each theory works, what evidence supports or challenges it, and whether any of these methods might actually be achievable. You'll learn about the paradoxes that time travel creates and the ingenious solutions physicists have proposed. So buckle up. We're about to explore one of physics' most mind-bending frontiers, the science of traveling through time. Before we dive into specific time travel theories, we need to understand what time actually is. This might seem like a simple question, but it's one that has puzzled philosophers and physicists for millennia. In everyday life, we think of time as something that flows steadily forward, like a river carrying us from past to future. We measure it with clocks, organize our lives around it, and feel its passage with every birthday. But physics reveals that time is far stranger than our intuition suggests. In classical physics, the physics of Newton that dominated science for centuries, time was considered absolute and universal. No matter where you were in the universe or how fast you were moving, time ticked forward at the same rate for everyone. A second on Earth was the same as a second on Mars, on a distant star, or aboard a speeding spaceship. Time was like a cosmic clock that synchronized everything in the universe. Then Albert Einstein changed everything. In 1905, Einstein published his theory of special relativity, and with it, he shattered our understanding of time. Special relativity was born from a deceptively simple observation. The speed of light is constant for all observers, regardless of how fast they're moving. This seems innocent enough, but it has profound implications. Imagine you're on a train moving at half the speed of light, and you shine a flashlight forward. Common sense says the light from your flashlight should travel at the speed of light plus the speed of the train. But Einstein showed that's not what happens. An observer standing beside the tracks would measure that light traveling at exactly the speed of light, no faster. The speed of light, roughly 300,000 kilometers per second, is a universal speed limit that never changes. But if the speed of light is constant for everyone, something else has to give. That something is time itself. Special relativity reveals that time is not absolute. It's relative. Time passes at different rates, depending on how fast you're moving. This is the foundation of time travel to the future, and it's not science fiction, it's proven fact. Here's how it works. Imagine two twins, Alice and Bob. Alice stays on Earth, while Bob boards a spaceship and travels at 90% of the speed of light to a distant star and back. The journey takes Bob 10 years, according to his watch. But when he returns to Earth, he finds that Alice has aged not 10 years, but 23 years. Bob has literally traveled into Earth's future. This isn't a trick or an illusion. Time genuinely passed more slowly for Bob because he was moving at such high speeds. This effect is called time dilation, and we can calculate it precisely using Einstein's equations. The faster you move, the more extreme the effect becomes. At 99% of the speed of light, time slows to about 1/7 its normal rate. At 99.9%, it slows to about 1/22. We've confirmed time dilation countless times. Atomic clocks flown on airplanes show measurably less elapsed time than identical clocks that stayed on the ground. GPS satellites orbiting Earth experience time differently than we do on the surface, and their systems must account for this, or navigation would be impossibly inaccurate. Particles called muons, created in Earth's upper atmosphere, shouldn't survive long enough to reach the ground based on their short lifespans, but they do, because they're moving so fast that time slows down for them. Special relativity deals with objects moving at constant speeds. But in 1915, Einstein published an even more revolutionary theory, general relativity. This theory extended his ideas to include acceleration and gravity, and in doing so, it completely reimagined the structure of the universe. General relativity's central insight is that gravity isn't a force in the traditional sense. Instead, massive objects bend and warp the very fabric of space and time. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it curves toward the bowling ball, following the contour of the warped sheet. This is essentially how gravity works, except instead of a rubber sheet, we're talking about space-time itself. Space-time is the key concept here. Before Einstein, physicists thought of space and time as separate entities. Space was the three-dimensional arena where events happened, and time was the universal clock that measured when they happened. Einstein showed they're actually inseparable, two aspects of a single four-dimensional fabric called spacetime. You can think of spacetime as a vast cosmic tapestry woven from 3 dimensions of space and 1 dimension of time. Every event that has ever happened or will happen exists as a point in this 4-dimensional fabric. When you move through space, you're also moving through time. And when massive objects like stars, planets, or black holes exist, they create curves and valleys in this fabric. This warping of space-time explains gravity. Earth doesn't pull on you with a mysterious force. Instead, Earth's mass curves space-time around it, and you follow the natural contours of that curved space-time. From your perspective, you feel this as gravity pulling you down. But from the perspective of space-time itself, you're simply following the straightest possible path, through curved geometry. Here's where things get interesting for time travel. Gravity doesn't just curve space. It curves time too. The stronger the gravitational field, the slower time passes. This is called gravitational time dilation, and it's distinct from the velocity-based time dilation we discussed earlier. Near a massive object like Earth, time passes slightly slower than it does far away in deep space. The effect is small on Earth. Clocks at sea level run slightly slower than clocks on mountaintops, but it's measurable and real. Near an incredibly massive object like a neutron star or black hole, the effect becomes dramatic. Imagine standing near the edge of a black hole's event horizon, the point of no return beyond which nothing can escape. Time would slow down so dramatically that if you watch someone far away from the black hole, they would appear to be moving in fast motion. Years might pass for them, while only minutes pass for you. And if they watched you, you would appear nearly frozen, moving in extreme slow motion. This gives us our second method of time travel to the future. Instead of moving at high speeds, you can park yourself near a massive object where gravity is intense. Stay there for what feels like a few years, then return to normal space. Decades or centuries might have passed for the rest of the universe. You've jumped into the future without moving at high speed. Both time dilation effects, from velocity and from gravity, allow forward time travel. They're not speculation. They're established physics, confirmed by countless experiments and observations. We use these effects in practical technology every single day. Your smartphone's GPS wouldn't work without accounting for both types of time dilation affecting the satellites orbiting Earth. But forward time travel, while fascinating, is the easy part. The real mystery, the true frontier of physics, is backward time travel. Can we journey into the past? This is where Einstein's equations become truly strange. General relativity doesn't explicitly forbid backward time travel. In fact, the equations allow for solutions where time loops back on itself, creating what physicists call closed time-like curves. These are paths through spacetime that circle back to their starting point in time, like a highway that eventually returns you to your own past. The mathematics permits these solutions, but do they exist in reality? Can nature actually create pathways to the past? Or do deeper principles of physics forbid it? These questions drive much of modern theoretical physics, and they're what make time travel theories so compelling. Understanding spacetime, relativity, and time dilation is essential for everything that follows. Every time travel theory we'll explore builds on these foundations. Some theories use extreme velocities or gravitational fields. Others exploit exotic features of spacetime geometry. A few venture into quantum mechanics, where reality becomes even stranger. The crucial point is this: time is not the rigid, universal entity we experience in everyday life. It's flexible, stretchable, and intimately connected to space and gravity. This flexibility opens the door to possibilities that would have seemed absurd just over a century ago. Time travel isn't just a fantasy dreamed up by science fiction writers. It emerges naturally from our best understanding of how the universe works. Now that we understand the foundation, what time is, how it can be stretched and warped, we're ready to explore the specific theories that might allow us to exploit these properties. Some will seem almost plausible. Others will require technology or conditions so extreme they may be forever beyond our reach. But all of them are grounded in real physics, emerging from the same equations that explain the orbit of planets, the bending of starlight, and the ticking of your watch. Let's begin with the most mathematically rigorous time travel theories, those that emerge directly from Einstein's general relativity. These aren't wild speculations. They're legitimate solutions to Einstein's field equations, the same equations that accurately describe gravity, planetary orbits, and the expanding universe. The fact that these equations permit time travel is both thrilling and deeply puzzling to physicists. At the heart of many time travel theories lies a concept called closed time-like curves, or CTCs. To understand what this means, we need to talk about world lines. In the four-dimensional space-time we discussed earlier, every object traces a path through space and time. This path is called a world line. Your world line is the complete record of everywhere you've been and when you were there, stretching from your birth into your future. Normally, world lines point steadily forward in time. You can move in any direction through space, left, right, forward, backward, up, down, but you always move forward through time. Your world line never loops back to an earlier moment. But general relativity allows for special configurations of spacetime where world lines can form closed loops. These are closed time-like curves, paths through spacetime that eventually return to their starting point in both space and time. If you could follow a CTC, you would journey forward through space and time, but eventually arrive back at the exact moment you left. You would meet your past self. CTCs sound impossible, but they're mathematically valid solutions to Einstein's equations under certain conditions. The question isn't whether the math allows them, it does. The question is whether nature actually creates the extreme conditions necessary for CTCs to exist, and whether the laws of physics permit them in practice even if the equations suggest they're possible in theory. Several of the theories we'll explore involve creating or exploiting CTCs. They represent the mathematical foundation for backward time travel within general relativity. Now let's talk about wormholes. perhaps the most famous time travel mechanism in both science and science fiction. Wormholes, also called Einstein-Rosen bridges, are theoretical tunnels through spacetime that connect two distant points. Imagine folding a piece of paper so two points touch, then punching a hole through both layers. Instead of traveling across the paper surface, you could take a shortcut through the hole. That's essentially what a wormhole does with spacetime. Einstein and physicist Nathan Rosen discovered the possibility of wormholes in 1935 while studying the equations of general relativity. They found that the curved spacetime around a black hole could theoretically connect to another region of spacetime through a bridge or tunnel. This Einstein-Rosen bridge would provide a shortcut between two points that might be separated by vast distances or even different times. Here's how a wormhole could enable time travel. First, you'd need a traversable wormhole, one that doesn't crush you with infinite gravity or snaps shut before you can pass through. The original Einstein-Rosen bridges weren't traversable. They'd collapse instantly if anything tried to enter them. But in 1988, physicists Kip Thorne and Michael Morris showed that with exotic matter with negative energy density, a wormhole could theoretically be held open and made safe to traverse. Once you have a traversable wormhole with two mouths, let's call them entrance A and exit B, you could turn it into a time machine using time dilation. Here's the trick. Take mouth B and accelerate it to near light speed, then bring it back. Remember our discussion of time dilation? Time passes more slowly for objects moving at high speeds. So while you're accelerating mouth B, less time passes for it than for mouth A, which stayed stationary. Now the two mouths of the wormhole are at different times. Step through mouth A, and you emerge from mouth B. But in the past, relative to mouth A's timeline, you've traveled backward through time. The wormhole has become a time machine. This isn't just creative speculation. It's based on rigorous calculations using general relativity. The catch, and it's a big one, is that we've never observed exotic matter with negative energy density in the quantities required. Quantum effects can produce tiny amounts of negative energy, but scaling this up to wormhole size is currently beyond our understanding. Some physicists argue that the laws of quantum mechanics might fundamentally forbid the large-scale negative energy needed for traversable wormholes. There's another problem too. Even if you could create a wormhole time machine, you couldn't travel to a time before the time machine was built. The wormhole must exist for the entire span of time you want to access. So wormhole time machines wouldn't let you visit the dinosaurs or meet Shakespeare, but they might let future civilizations visit us. Let's move to one of the most fascinating objects in the universe, rotating black holes, also called Kerr black holes, named after physicist Roy Kerr, who discovered their mathematical description in 1963. While regular black holes are spherical and static, rotating black holes spin, and this spin dramatically changes their internal structure. When a massive star collapses into a black hole, it retains its angular momentum, its spin. This creates a black hole that rotates, dragging space-time around with it like a vortex. The faster it spins, the more extreme the effects become. At the center of a regular black hole sits a point of infinite density, called a singularity. But in a rotating black hole, the singularity isn't a point, it's a ring. This ring singularity is where things get weird. Physicists studying the mathematics of Kerr black holes discovered that you could theoretically pass through the ring singularity without being destroyed. On the other side, you might emerge into a different region of spacetime, possibly a different universe, or possibly a different time in our own universe. The equations suggest that the region inside a rotating black hole contains closed time-like curves. If you could navigate through a Kerr black hole without being torn apart by gravitational forces, you might follow one of these CTCs and emerge in your own past. The rotating black hole would function as a natural time machine. However, there are serious questions about whether this is physically possible. The interior of a black hole is one of the most extreme environments conceivable. Tidal forces, differences in gravitational pull across your body, would likely shred any physical object long before it reached the ring singularity. Additionally, physicist Roger Penrose suggested that entering a spinning black hole might trigger an instability that causes it to collapse before you could pass through. The ring singularity itself might be unstable and unable to exist in our universe. Still, curved black holes demonstrate that general relativity naturally produces solutions containing time travel. Whether nature allows these solutions to exist in practice remains an open question. Now we come to the Tipler cylinder, one of the most fascinating and strange time travel proposals. In 1974, physicist Frank Tipler discovered that an infinitely long, incredibly dense cylinder rotating at nearly the speed of light could create closed time-like curves in the surrounding spacetime. Imagine a cylinder of incredibly dense matter, perhaps as dense as a neutron star, stretched out to infinite length. Now spin this cylinder at a significant fraction of light speed. The rotation drags spacetime around with it, creating a swirling vortex of curved spacetime. Tipler's calculations showed that if you traveled in a specific spiral path around this rotating cylinder, you would eventually return to your starting point in both space and time. You'd have followed a closed time-like curve. The faster the cylinder spins, the easier it becomes to travel back in time. The denser it is, the more it curves spacetime. In principle, if you could build such a cylinder and set it spinning, you could use it as a time machine to visit any point in time after its construction. Of course, the practical challenges are absurd. You'd need exotic matter denser than anything we've ever encountered, arranged in an infinitely long cylinder, which is impossible in a finite universe. You'd need to spin it at tremendous speeds without it tearing itself apart. And even if you could build one, it would create such extreme gravitational effects that it might be dangerous to the fabric of spacetime itself. The Tipler cylinder serves more as a theoretical demonstration that general relativity permits time travel under certain conditions, rather than as a practical blueprint. It shows that the equations don't inherently forbid backward time travel. Nature might still forbid it through other means, but the fundamental framework of general relativity leaves the door open. Related to the Tipler cylinder is the Gödel metric, discovered by mathematician Kurt Gödel in 1949. Gödel found an exact solution to Einstein's field equations, describing an entire universe that rotates. In Gödel's rotating universe, closed time-like curves exist everywhere. At any point in this universe, you could, in principle, journey into your own past. Gödel's solution was revolutionary because it showed that time travel might be a fundamental property of the universe's structure, not just a feature of exotic objects like black holes or hypothetical cylinders. In a Gödel universe, time travel would be as natural as space travel. The catch is that our universe doesn't appear to be a Gödel universe. Observations show that our universe is expanding uniformly in all directions, not rotating. If the universe were rotating as Gödel's solution requires, we'd observe systematic patterns in the distribution and motion of galaxies. We don't see such patterns. Our universe seems to be the non-rotating type, where closed time-like curves don't naturally exist everywhere. Still, Gödel's work was philosophically profound. It showed that time travel doesn't violate the fundamental laws of general relativity. It raised deep questions about the nature of time, and whether the universe we happen to inhabit is the only type permitted by physics, or if we simply live in one of many possible configurations. Now let's discuss one of the most intriguing modern proposals, the Alcubierre drive. In 1994, physicist Miguel Alcubierre discovered a solution to Einstein's equations that would allow faster-than-light travel without violating relativity. The key insight is that while nothing can move through space faster than light, space itself can expand or contract at any rate. The Alcubierre drive works by contracting spacetime in front of a spacecraft and expanding it behind. The ship sits in a bubble of flat spacetime that moves by surfing this wave of contracting and expanding space. From the ship's perspective, it never exceeds light speed locally. Space is moving, not the ship. But from an outside perspective, the ship could traverse vast distances in arbitrarily short times, effectively traveling faster than light. Now here's where time travel enters the picture. Special relativity tells us that anything moving faster than light would also be moving backward in time from certain reference frames. If you could travel faster than light using an Alcubierre drive, you could potentially arrange your journey to arrive at your destination before you left, traveling into the past. The physics here gets complicated and involves carefully arranging multiple faster-than-light journeys between reference frames, but the fundamental principle is sound. Faster-than-light travel enables time travel. The Alcubierre drive would be a time machine. Unfortunately, the Alcubierre drive faces the same obstacle as traversable wormholes. It requires enormous amounts of exotic matter with negative energy density. Initial calculations suggested you'd need more negative energy than exists in the entire visible universe. Later refinements reduced this requirement, but it's still far beyond anything we can produce. Some physicists argue that quantum field theory might fundamentally prohibit the creation of such large quantities of negative energy. There's another problem too. You'd need to set up the bubble of warp spacetime before entering it. This means you couldn't use an Alcubierre drive to reach anywhere you hadn't already sent the bubble preparation equipment to at slower than light speeds. Like wormhole time machines, it wouldn't let you visit times before the technology was developed. Finally, let's explore cosmic strings, hypothetical topological defects in spacetime that might have formed during the first moments after the Big Bang. Think of them as incredibly thin cracks or imperfections in the fabric of spacetime itself, somewhat like the cracks that form in ice as water freezes. Cosmic strings, if they exist, would be unimaginably dense. A single cosmic string with the width of a human hair could have more mass than Earth. This extreme density would create powerful gravitational effects, warping spacetime around them dramatically. In 1991, physicist Richard Gott showed that if two cosmic strings passed by each other at high speeds, the warp spacetime around them could create closed time-like curves. By flying a carefully planned path around the two passing strings, you could exploit these CTCs to travel back in time. The amount of time travel possible depends on how fast the strings are moving relative to each other and how close together they pass. Faster moving strings or closer passes would allow you to travel further into the past. You'd need the strings to be moving at a significant fraction of light speed and passing within a relatively short distance of each other. The problem is that we've never detected a cosmic string. They're purely hypothetical objects predicted by certain theories of the early universe. Even if they exist, they're probably extremely rare. And even if you could find two cosmic strings, getting them to pass each other at the right speeds and distances would require technology to move objects with the mass of entire galaxies. Clearly impossible. Like many of these theories, cosmic strings demonstrate that general relativity permits time travel under certain extreme conditions. The universe might contain natural time machines in the form of cosmic strings, though we have no evidence they exist. Each of these general relativity-based theories shares common features. They're all mathematically valid solutions to Einstein's equations. They all require extreme conditions, exotic matter, infinite structures, immense energies, or very specific cosmic objects. And they all face serious questions about whether nature actually permits these conditions to exist. Some physicists believe there must be a deeper principle that forbids time travel, even though general relativity seems to allow it. Others think time travel might be possible, but forever beyond our technological reach. A few optimists believe that sufficiently advanced civilizations might one day harness these effects. What's clear is that general relativity opened a door that Newton's physics had kept firmly shut. Time travel isn't just fantasy. It emerges naturally from our best theory of gravity and space-time. Whether that door leads anywhere remains one of physics' greatest mysteries. While general relativity provides some of the most rigorous time travel theories, it's not the only framework that suggests time travel might be possible. When we venture into the realm of quantum mechanics and particle physics, we encounter entirely different approaches to manipulating time. These theories operate at the smallest scales of reality, where the rules that govern everyday objects break down completely. Quantum mechanics is strange. It's a world where particles can exist in multiple states simultaneously, where the act of observation changes reality, and where cause and effect become fuzzy concepts. In this bizarre realm, physicists have discovered phenomena that might allow for time travel in ways that have nothing to do with warping spacetime. Let's start with one of the most speculative ideas, tachyons. The name comes from the Greek word tachys, meaning swift. Tachyons are hypothetical particles that always travel faster than light, not particles that accelerate to light speed. Particles that can never slow down below light speed. They would be permanently locked in the faster-than-light realm. Why would faster-than-light particles enable time travel? It comes back to special relativity. Einstein showed that as objects approach light speed, time slows down for them. At exactly light speed, time would stop. The equation suggests that if something could exceed light speed, time would run backward for it. A tachyon moving through space would effectively be moving backward through time. If tachyons exist, you might be able to use them to send information into the past. Imagine building a tachyon transmitter and receiver. You send a tachyon signal today, and because tachyons travel backward in time, the signal arrives yesterday. You've transmitted information to the past. With such a device, you could theoretically send messages to your earlier self, warning about future events or providing winning lottery numbers. The problem is that we've never detected tachyon. Every search has come up empty. Moreover, tachyons create severe paradoxes. If you could send information to the past, you could create causal loops where effects precede their causes. You could send yourself a message telling you not to send a message, creating a logical contradiction. Many physicists believe tachyons probably don't exist. The mathematics of special relativity technically allows for them, but that doesn't mean nature permits them. Just because an equation has a solution doesn't guarantee that solution corresponds to physical reality. Tachyons might be mathematical artifacts rather than real particles. There's another issue too. Even if tachyons exist, their properties would be bizarre. They would have imaginary mass, not negative mass, but mass whose value involves the square root of -1. It's unclear what imaginary mass even means physically, or whether such particles could interact with normal matter in any useful way. Now let's discuss one of the most elegant ideas in physics, the Dirac antiparticle interpretation. In 1928, physicist Paul Dirac developed an equation describing electrons that incorporated both quantum mechanics and special relativity. The Dirac equation was remarkably successful, but it had a strange feature. It predicted particles with negative energy. Negative energy particles were puzzling. Dirac realized these solutions corresponded to antimatter, particles identical to electrons but with opposite electric charge. He predicted the existence of positrons, the antimatter counterpart to electrons, and they were discovered 4 years later. This was one of physics' greatest triumphs. But Dirac noticed something fascinating about the mathematics. You could interpret antiparticles in 2 equivalent ways. The standard interpretation is that a positron is a distinct particle moving forward through time. The alternative interpretation is that a positron is an electron moving backward through time. Think about that. When a positron moves from point A to point B, you could equally well describe it as an electron moving from B to A, but backward in time. The mathematics works out identically. It's just 2 different ways of describing the same physical process. This interpretation provides a beautiful explanation for why particles and antiparticles have opposite charges. If an electron is moving backward in time, its charge would appear reversed from our perspective. Time-reversed motion flips the sign of electric charge. Physicist Richard Feynman developed this idea further in his formulation of quantum electrodynamics. Feynman diagrams, the pictures physicists use to calculate particle interactions, explicitly treat antiparticles as particles moving backward through time. This isn't just a curiosity. It's a computational tool that makes calculations easier. However, this doesn't mean you can use antiparticles to send messages to the past or travel backward in time yourself. The backward in time description is a mathematical perspective, not a practical time machine. From the antiparticle's perspective, it's moving forward in time just like everything else. The time reversal interpretation is a useful mathematical trick, but it doesn't give us control over time's direction. Still, the Dirac interpretation is philosophically profound. It suggests that at the quantum level, the distinction between forward and backward in time might be more flexible than we think. Time symmetry, the idea that physical laws work the same backward and forward, is a fundamental principle in particle physics. The Dirac interpretation makes this symmetry manifest in the structure of reality itself. Moving to perhaps the most mind-bending approach to time travel, we come to Hugh Everett's many worlds interpretation of quantum mechanics. This interpretation addresses one of quantum mechanics' deepest mysteries. What happens when you measure a quantum system? In quantum mechanics, particles don't have definite properties until you measure them. An electron isn't in a specific location. It exists in a superposition of many possible locations simultaneously. When you measure its position, the superposition collapses, and the electron appears in one specific location. But which location? The theory only predicts probabilities. The standard Copenhagen interpretation says the measurement causes the wave function to collapse randomly, selecting one outcome. But Everett proposed something radically different. Nothing collapses. Instead, every possible outcome actually occurs, each in its own separate branch of reality. When you measure the electron, the universe splits. In one branch, you find it in location A. In another branch, you find it in location B. In yet another branch, location C. All possibilities are realized, each in its own parallel universe. You only experience one branch, but copies of you in other branches experience different outcomes. This is the many worlds interpretation, and it has profound implications for time travel. If every quantum event causes the universe to branch, then time travel to the past doesn't create paradoxes. It just creates new branches. Imagine you travel back in time and prevent your grandfather from meeting your grandmother. In the standard timeline, you were never born, creating the grandfather paradox. But in many worlds, your action creates a new branch where you were never born. The original timeline still exists as a separate branch where you were born and eventually traveled back in time. No paradox occurs because you don't erase your own timeline. You just create a new branch that diverges from it. This resolves the most troubling objections to time travel. Every potentially paradoxical action simply creates a new branch of reality. You can kill your grandfather, prevent your own birth, or stop yourself from entering the time machine. Each action generates a new timeline where those events unfold, while the original timeline remains intact. Many worlds provide a framework where time travel could be logically consistent. However, it doesn't tell us how to actually achieve time travel. It's a solution to the paradox problem, not a blueprint for building a time machine. You'd still need something like a wormhole or a Tipler cylinder to actually travel through time. Many worlds just ensures that if you could travel to the past, you wouldn't destroy the logical consistency of the universe. The many worlds interpretation is controversial. Some physicists embrace it as the most natural way to understand quantum mechanics. Others find it absurdly extravagant. Why multiply universes endlessly when simpler explanations might suffice? The interpretation makes no unique predictions that differ from standard quantum mechanics, so we can't test whether it's correct. It remains a philosophical position about what quantum mechanics means, rather than a testable scientific theory. Finally, we come to quantum gravity approaches to time travel. Quantum gravity is the holy grail of modern physics, a theory that unifies quantum mechanics and general relativity. We have two spectacularly successful theories. General relativity describes gravity and space-time at large scales, while quantum mechanics describes matter and energy at small scales. But the two theories are fundamentally incompatible. At everyday scales, we can use general relativity for gravity and quantum mechanics for atoms, and we never notice the incompatibility. But in extreme situations, inside black holes, at the moment of the Big Bang, or at distant scales smaller than the Planck length, both quantum effects and gravitational effects become important. In these regimes, we need a unified theory, and we don't have one yet. Several approaches to quantum gravity have been proposed: string theory, loop quantum gravity, causal set theory, and others. Each approach treats space-time and time differently at the quantum level, and some of these approaches have interesting implications for time travel. In some versions of quantum gravity, space-time might not be continuous at the smallest scales. Instead, it might be made of discrete chunks, like pixels on a screen. If space-time is fundamentally granular, the notion of continuous world lines and closed time-like curves might not apply at the Planck scale. Time travel might be fundamentally impossible at quantum scales, even if general relativity permits it at larger scales. Other approaches suggest that time itself might emerge from more fundamental quantum processes. In some formulations of quantum gravity, time isn't a fundamental feature of reality. It's an emergent property that arises from quantum entanglement and other quantum phenomena. If time is emergent, then traveling through time might be as meaningless as traveling through temperature or pressure. You can't move, through something that isn't fundamentally real. Some quantum gravity theories suggest that tiny wormholes might exist naturally at the quantum scale, fluctuating in and out of existence due to quantum foam, the roiling uncertainty that dominates physics at the Planck length. These quantum wormholes would be far too small to travel through, but they might allow information to leak between different times or places in microscopic amounts. This could have subtle effects on causality at quantum scales. The Novikov self-consistency principle, proposed by physicist Igor Novikov, offers another quantum approach to time travel. Novikov suggested that quantum mechanics might automatically prevent paradoxes. If you tried to travel back and create a paradox, quantum effects would conspire to stop you. The probability of paradox-generating actions would be exactly zero. In this view, you could travel to the past, but you'd find yourself unable to change anything in a way that creates a logical contradiction. If you tried to shoot your grandfather, the gun would jam, or you'd miss, or something would always intervene. Not because of luck or coincidence, but because the quantum wave function contains only possibilities that are self-consistent. Paradoxical timelines have zero probability in the sum over histories calculation. This principle is speculative and hasn't been proven, but it shows how quantum mechanics might naturally resolve time travel paradoxes without requiring many worlds or other elaborate interpretations. The truth is that we don't yet have a complete theory of quantum gravity, so all of these ideas remain tentative. We're working at the frontier of human knowledge, trying to understand how reality behaves in conditions we can't yet test experimentally. Time travel at quantum scales remains an open question that will likely only be resolved when we finally develop a successful theory of quantum gravity. What these quantum and particle theories show is that time travel isn't just about warping spacetime. The quantum realm offers alternative pathways, alternative frameworks, and alternative ways of thinking about cause, effect, and the nature of time itself. Whether any of these quantum approaches ultimately prove correct, they demonstrate that our understanding of time remains incomplete. The deepest truths about time, and whether we can truly travel through it, might not come from studying black holes and cosmic strings, but from understanding the bizarre quantum dance that underlies all of reality. Beyond the well-established theories of general relativity and the speculative ideas from quantum mechanics, there are several experimental and more speculative approaches to time travel. Some of these build on confirmed physical phenomena, while others venture into territory where physics becomes highly uncertain. Let's explore these frontier ideas that push the boundaries of what might be possible. We've already discussed how approaching light speed causes time dilation. Time passes more slowly for you relative to stationary observers. This is the most accessible form of time travel we know exists. It's not hypothetical. It's not speculative. It's confirmed physics that we observe and measure regularly. Astronauts on the International Space Station experience this effect right now. Because they're orbiting Earth at about 28,000 kilometers per hour, time passes slightly more slowly for them than for people on the ground. After 6 months in orbit, an astronaut has aged about 0.007 seconds, less than if they'd stayed on Earth. It's a tiny amount, but it's real, measurable time travel into the future. The effect becomes dramatic as you approach light speed. At 90% of light speed, time slows to about 44% of normal. Travel for 5 years at this speed, and 11 years pass on Earth. At 99% of light speed, the effect is even more extreme. Your 5 years equals about 35 years on Earth. At 99.9%, your 5 years equals over 100 years on Earth. This is genuine time travel to the future. If we could build a spacecraft capable of reaching these speeds, we could send people centuries or millennia into Earth's future. They'd experience the journey as taking only years, but they'd arrive in a far future Earth that had aged much more. The obstacles are technological, not fundamental physics. Accelerating something as massive as a spacecraft to near light speed requires staggering amounts of energy. Using conventional rocket fuel is completely impractical. You'd need fuel that weighs more than the observable universe to accelerate even a small spacecraft to 99% of light speed using chemical rockets. More exotic propulsion methods might work. Nuclear fusion rockets, antimatter engines, or photon sails, pushed by powerful lasers, could potentially reach significant fractions of light speed given enough time and resources. Some physicists have proposed interstellar ramjets that scoop up hydrogen from space and fuse it for fuel, potentially allowing sustained acceleration to very high speeds. The point is that light-speed time travel isn't about discovering new physics. We know it works. The challenge is engineering. A sufficiently advanced civilization could definitely use this method to travel into the future. Whether we'll achieve it depends on technological progress, not on whether the physics permits it. Now let's discuss neutron stars, some of the densest objects in the universe. When a massive star explodes as a supernova, its core can collapse into a neutron star, an object about 20 kilometers across but containing more mass than the Sun. The density is incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons. This extreme density creates extreme gravity. The gravitational field at the surface of a neutron star is about 200 billion times stronger than Earth's gravity. This immense gravity causes severe gravitational time dilation. Time passes much more slowly near a neutron star than it does in flat spacetime far away. If you could somehow survive near a neutron star, the gravity would crush anything made of ordinary matter. You could use it as a time machine to the future. Park yourself in orbit close to the neutron star. Wait what feels like a year, then return to Earth. Depending on how close you got and how strong the time dilation effect was, decades or centuries might have passed on Earth. Neutron stars aren't as extreme as black holes, so they don't create closed time-like curves or allow backward time travel. But they're real objects that we've observed throughout the universe. We know thousands of neutron stars exist. Using them for time travel is theoretically possible, though the engineering challenges would be formidable. You'd need shielding against the neutron stars' intense magnetic fields, which can be trillions of times stronger than Earth's. You'd need a propulsion system powerful enough to escape the gravitational pull when you wanted to leave. You'd need to protect yourself from the radiation and extreme tidal forces. But unlike wormholes or Tipler cylinders, neutron stars actually exist. They're not hypothetical constructs requiring exotic matter or impossible engineering. They're real objects we could potentially visit with sufficiently advanced technology. Black holes in general, not just the rotating curve black holes we discussed earlier, also create extreme time dilation. Even a non-rotating black hole warps time dramatically near its event horizon. The closer you get to the event horizon, the slower time passes for you relative to distant observers. This creates a dramatic effect visible from the outside. If you watch someone fall toward a black hole's event horizon, you'd see them slow down as they approached it. Their movements would become sluggish. Light from them would redshift, becoming dimmer and redder. They would appear to freeze at the event horizon, never quite crossing it, their image fading slowly over time. From the falling person's perspective, time passes normally. They cross the event horizon in finite time according to their watch. But from your distant perspective, you'd see them taking infinite time to cross. This is gravitational time dilation at its most extreme. You could use this effect for time travel. Instead of falling into the black hole, you orbit close to the event horizon for what feels like a short time, then escape using powerful rockets. When you return to flat spacetime, you'd find that far more time has passed for the rest of the universe. You've traveled to the future. The closer you orbit to the event horizon, the stronger the effect. Orbit just above the event horizon of a supermassive black hole, the kind found at the centers of galaxies, and time could slow dramatically. The movie Interstellar depicted this scenario. Astronauts visiting a planet orbiting close to a black hole found that 1 hour on the planet equaled 7 years back on Earth. The physics of this scene was actually quite accurate, based on calculations by physicist Kip Thorne. Like neutron stars, black holes actually exist. We've detected them throughout the universe, from stellar mass black holes formed by collapsing stars to supermassive black holes millions or billions of times the sun's mass. Using them for time travel is theoretically possible with the right technology. The challenges are severe. You need enormous energy to orbit so close to a black hole without falling in. You need to avoid the intense radiation from matter falling into the black hole, which forms a superhot accretion disk. You need protection from tidal forces. But these are engineering problems, not fundamental physics problems. Now we come to exotic matter, which we've mentioned several times already. Exotic matter is material with negative energy density or negative mass. It's the key requirement for many time travel schemes, particularly traversable wormholes and the Alcubierre drive. Normal matter has positive energy. Exotic matter would have negative energy. This sounds impossible, but quantum mechanics actually predicts tiny amounts of negative energy in certain situations. The Casimir effect is one example. Place two uncharged metal plates very close together in a vacuum, and quantum fluctuations create a region between the plates with slightly negative energy density. The negative energy creates a small attractive force between the plates, which has been measured experimentally. So negative energy exists. The question is whether we can create it in large enough quantities to be useful for macroscopic effects like holding open a wormhole. The amounts produced in the Casimir effect are minuscule, nowhere near enough for time travel applications. Some physicists argue that quantum field theory might have built-in restrictions that prevent large accumulations of negative energy. These restrictions, called quantum inequalities, might ensure that while you can create negative energy in small regions for short times, you can't accumulate enough to build a time machine. Nature might have a cosmic protection mechanism that prevents us from exploiting negative energy for macroscopic purposes. Other physicists are more optimistic. They suggest that sufficiently advanced technology might find loopholes in the quantum inequalities or discover new forms of exotic matter that we haven't imagined yet. The early universe, during inflation, might have produced exotic matter that still exists somewhere. Advanced civilizations might harvest or manufacture exotic matter in ways we can't currently conceive. Exotic matter theory isn't really a separate time travel theory. It's a component of many time travel theories. Without exotic matter, traversable wormholes collapse. Without it, Alcubierre drives can't function. It's the missing ingredient that could turn several theoretical time machines into practical ones, if it can exist in sufficient quantities. Finally, let's discuss two highly speculative proposals: cesium laser theory and elementary particle ring and laser theory. These are less well-known and more controversial than the theories we've discussed so far. The cesium laser approach builds on experiments showing that light can be manipulated to travel at unusual speeds through certain media. In 2000, physicists managed to slow light to about 17 meters per second passing through ultra-cold cesium atoms. Other experiments have made light appear to travel faster than normal, or even backward, through careful manipulation of its properties. These experiments involve what's called group velocity, the speed at which the peak of a light pulse travels, versus phase velocity, the speed at which the wave pattern travels. By manipulating atomic properties with lasers, you can make the group velocity exceed the speed of light, or even become negative. Some speculative proposals suggest that if you could create extreme enough conditions, perhaps using powerful lasers and exotic atomic states, you might create regions where time itself flows differently. The idea would be to create a localized bubble where time manipulation becomes possible due to extreme effects on light propagation. However, these experiments don't actually violate relativity. The speed of light, the true universal speed limit, remains constant. What changes is how light propagates through a medium, which is a different phenomenon. Information still can't travel faster than light in vacuum, which means causality is preserved. Most physicists are skeptical that these effects could lead to actual time travel. Similarly, elementary particle ring and laser theory involves proposals to use particle accelerators, like the Large Hadron Collider, in combination with powerful lasers to create extreme conditions that might warp spacetime on small scales. The idea is that by concentrating enormous energy in a tiny region, you might create microscopic effects similar to those near black holes or other extreme gravitational sources. Particle accelerators create immense energies when particles collide, but even the most powerful accelerators operate far below the energies needed to create significant gravitational effects. The Planck energy, the scale where quantum gravity becomes important, is about 10 million trillion times higher than anything we can achieve with current technology. Warping space-time enough to create time travel would require energies closer to the Planck scale. Some speculative proposals suggest using lasers to further concentrate energy, or using the particle rings as components of larger systems that might amplify gravitational effects. But these remain highly speculative ideas, without clear theoretical foundations. No mainstream physics papers have demonstrated how such systems could actually create time travel. These experimental approaches represent the frontier where physics meets engineering speculation. Some of them, like light-speed time travel using relativistic spacecraft, are grounded in solid physics, but require enormous technological advances. Others, like exotic matter production or particle-accelerator time machines, push into territory where we're not even sure the physics allows what's being proposed. What unites all these approaches is that they're trying to find practical pathways to time travel using methods that might someday be achievable, rather than relying purely on natural cosmic structures or purely theoretical constructs. They represent humanity's attempt to take control of time, to engineer it rather than just understand it theoretically. Whether any of these experimental approaches will ultimately succeed remains unknown, but they show that the dream of time travel continues to inspire researchers to push the boundaries of technology and physics, searching for any possible way to achieve what was once thought impossible. We've explored 17 different theories and approaches to time travel, from the mathematically rigorous to the highly speculative. But throughout our discussion, we've encountered a persistent shadow: the problem of paradoxes. Time travel, particularly to the past, creates logical contradictions that challenge our understanding of cause and effect. Let's examine these paradoxes, the problems they create, and the various solutions physicists have proposed. The most famous is the grandfather paradox. You travel back in time and prevent your grandfather from meeting your grandmother. They never marry, your parent is never born, and therefore you're never born. But if you were never born, you couldn't travel back in time to prevent their meeting. So they do meet, you are born, and you do travel back to prevent them, creating an endless logical loop with no consistent resolution. This paradox strikes at the heart of causality. In normal physics, causes precede effects. You flip a light switch, then the light turns on. The arrow of causality points forward in time. But with time travel, effects can precede their causes. You can prevent events that already led to you being able to prevent them. The logical structure of reality seems to collapse. Closely related is the bootstrap paradox, also called an ontological paradox. Imagine you travel back in time and give Shakespeare a book containing all his plays. Shakespeare copies the plays and publishes them as his own. But where did the plays originally come from? You got them from Shakespeare's published works, which he only published because you gave them to him. The information has no origin point. It exists in a causal loop with no beginning. Or consider this version. You travel back and teach Einstein the theory of relativity. Einstein publishes it. You learn it from his papers. You travel back and teach it to him. Who actually discovered relativity? The knowledge seems to create itself from nothing, bootstrapping into existence through a time loop. Then there's the predestination paradox, sometimes called a causal loop. You travel back in time to prevent a disaster, but your actions caused the very disaster you were trying to prevent. For example, you travel back to stop an assassination. Your appearance startles the assassin's would-be victim, who stumbles into the path of a bullet that would have missed. Your intervention guaranteed the outcome you wanted to prevent. These paradoxes have troubled physicists for decades. Several solutions have been proposed, each with different implications for the nature of time and reality. The first solution is the consistency principle, most clearly articulated in the Novikov self-consistency principle we mentioned earlier. This principle states that time travel is possible, but only self-consistent events can occur. If you travel to the past, you can only do things that are consistent with the timeline you came from. In this view, you could travel back to try to kill your grandfather, but you would inevitably fail. The gun would jam, you'd miss, you'd hesitate, or something would prevent the paradox. Not through luck, but through the fundamental structure of reality. Only self-consistent timelines are possible. Paradoxical timelines have zero probability. This sounds like fate or predestination, but it's actually about the logical structure of spacetime. In a universe with closed time-like curves, The history of the universe must be self-consistent when viewed as a complete four-dimensional block. Events can influence the past, but only in ways that don't create logical contradictions. Some physicists find this solution elegant. It preserves free will. You can try to create paradoxes, but ensures they always fail. Others find it unsatisfying. It seems to require a cosmic conspiracy, where everything conveniently prevents paradoxes, without explaining why this should be so. The second major solution is the many worlds interpretation we discussed earlier. Every time you travel to the past and take an action, you create a new branch of reality. You can kill your grandfather in the new branch without paradox, because you came from a different branch where he survived. In this framework, time travel doesn't change your past. It creates alternative pasts in new branches. You can never return to your original timeline. Once you travel to the past and do something, you're in a new branch forever. Your original timeline continues to exist as a separate branch where you disappeared into the time machine and never returned. This solution completely eliminates paradoxes, but at a high cost. It multiplies universes extravagantly and makes returning to your original timeline impossible. You can travel to the past, but you can never go home. Every time travel creates a permanent split, forever separating you from the world you came from. A third approach is chronology protection. Physicist Stephen Hawking proposed the chronology protection conjecture. The laws of physics prevent the formation of closed time-like curves, except possibly on microscopic scales. Nature itself forbids time travel to the past through some mechanism we haven't fully identified yet. Hawking argued that whenever you try to create a time machine, whether through wormholes, Tipler cylinders, or any other method, quantum effects would intervene to destroy it. Specifically, vacuum fluctuations would build up and create infinite energy densities at the moment the time machine was about to activate, destroying the apparatus. This is speculative, since we don't have a complete theory of quantum gravity to confirm it. But it's an appealing idea. Nature has a built-in protection mechanism against time travel paradoxes. The universe simply doesn't allow time machines to function, preventing paradoxes from arising in the first place. The fourth possibility is that time travel creates inconsistencies, and the universe simply doesn't care. Perhaps reality can tolerate logical contradictions. Perhaps our assumptions about consistency are too rigid. This is the most radical solution and the least popular among physicists. But some philosophers argue we shouldn't rule it out. Beyond paradoxes, time travel faces other profound problems. Energy requirements are staggering. To create a traversable wormhole, you need exotic matter in enormous quantities. To accelerate to near light speed, you need energies far beyond what current technology can provide. To warp spacetime significantly, you need to manipulate mass and energy on cosmic scales. These aren't just engineering challenges. They might be fundamental limitations. The laws of thermodynamics place constraints on how much energy can be concentrated in a given region. Quantum mechanics might prevent the creation of macroscopic amounts of exotic matter. The structure of spacetime itself might resist being warped in the ways required for time travel. There's also the problem of information. What happens to information in time loops? If you create a bootstrap paradox where information has no origin, have you violated the laws of thermodynamics? Information has entropy, and entropy is supposed to always increase. But information in a causal loop has no beginning, seeming to violate entropy laws. The problem of quantum mechanics and time travel remains largely unsolved. How does wave function collapse work if you can influence your own past? If you measure a quantum state, then travel back and change something before the measurement, what happens to the measurement result? Does it retroactively change? Do both results exist? Quantum mechanics and time travel don't play nicely together, and we lack a clear framework for combining them. Despite all these problems, research continues. Theoretical physicists keep exploring the mathematics of time travel, looking for new solutions to Einstein's equations or new approaches to quantum gravity that might shed light on whether time travel is truly possible. Experimental physicists are probing the limits of what's possible with current technology. They're studying the properties of exotic quantum states, investigating whether negative energy can be produced in useful amounts, testing the limits of time dilation effects. While no one is building a time machine, The research touches on fundamental questions about the nature of space-time and quantum mechanics. Looking to the future, several paths seem possible. The pessimistic view is that time travel to the past is simply impossible. There might be a theorem, a chronology protection theorem, that definitively proves time machines can't exist. We haven't found such a theorem yet, but it might be waiting to be discovered once we have a complete theory of quantum gravity. The moderately optimistic view is that time travel might be possible in principle, but forever beyond practical reach. The energy requirements, the exotic matter needed, the precision engineering required, all of it might be technically possible, but so difficult that even civilizations millions of years more advanced than us couldn't achieve it. Time travel would remain a theoretical curiosity, like a physical process that's allowed by the laws of physics, but never actually occurs in our universe. The optimistic view is that time travel is possible and achievable with sufficiently advanced technology. Perhaps in centuries or millennia, humanity or its descendants will master the manipulation of space-time, will create traversable wormholes, engineer Alcubierre drives, or discover entirely new approaches we haven't imagined yet. We'll find ways to produce exotic matter or work around the need for it. We'll solve the paradoxes through consistency principles or many-worlds or some framework we haven't conceived yet. If this optimistic future comes to pass, the implications would be staggering. History would become accessible. We could study the past directly, watching events unfold firsthand, rather than reconstructing them from fragmentary evidence. We could test historical theories, resolve mysteries, see how civilizations really developed. But we'd also face profound ethical questions. Should we interfere with past events? Even if we could only create new timeline branches, without affecting our own past, should we? What rights do the people in those new branches have? What responsibilities do we have toward timelines we create? If we could visit the future, what would we find? Would we discover that humanity flourishes, spreading across the galaxy? Or would we find that we destroyed ourselves through war, environmental collapse, or technological mishap? And if we found a terrible future, should we try to change it? Could we change it? Or would our attempts to alter the future only guarantee it unfolds as we foresaw? Time travel would also transform physics itself. If we could conduct experiments at different points in time, we could test theories in entirely new ways. We could observe the early universe directly, watching the Big Bang unfold. We could visit the far future to see how the universe ends. We could test whether physical constants have changed over cosmic time, whether the laws of physics are truly eternal, whether our theories are correct over all time scales. For now, these remain dreams and speculations. Time travel exists in the equations of physics, in the solutions to Einstein's field equations, in the strange predictions of quantum mechanics. It exists as a theoretical possibility, a logical consequence of our best understanding of nature. But whether it exists in practice, whether time machines can be built, whether paradoxes can be resolved, whether the universe permits us to manipulate time, remains unknown. What we've learned from studying time travel is that time itself is far stranger than we ever imagined. It's not the simple, universal clock that Newton envisioned. It's a flexible dimension of space-time, warped by gravity, dilated by motion, possibly quantized at the smallest scales, perhaps even emergent rather than fundamental. The study of time travel has deepened our understanding of causality, entropy, quantum mechanics, and the structure of the universe. Even if we never build a working time machine, the theoretical investigation has been profoundly valuable. It's pushed physics to confront its deepest assumptions about the nature of reality. So here we stand, over a century after Einstein revolutionized our understanding of time, with 17 different theoretical pathways to time travel laid out before us. Some are grounded in established physics, confirmed by countless experiments. Others are highly speculative, pushing the boundaries of what might be possible. Some might lead somewhere. Others might be dead ends. But all of them show that time travel isn't just science fiction. It's a legitimate subject of scientific inquiry, emerging naturally from our best theories of how the universe works. Whether we'll ever travel through time remains to be seen. Perhaps future physicists will prove it's impossible. Perhaps future engineers will build time machines. Perhaps the answer lies in physics we haven't discovered yet, in theories beyond general relativity and quantum mechanics that will revolutionize our understanding once again. Until then, we can marvel at how far we've come in understanding time, and we can dream about where we might go, not just in space, but in time itself. The journey to understand time travel has already taken us to fascinating places in physics and philosophy. Where it leads next is a story still being written, a future still unfolding, a mystery waiting to be solved. Thank you for joining us on this exploration of time travel theories. From the foundations of relativity to the frontiers of quantum mechanics, from cosmic strings to many worlds, we've covered the full spectrum of scientific thinking about one of humanity's oldest dreams. Whether time travel becomes reality or remains forever theoretical, the quest to understand it has already expanded our knowledge of the universe in profound and beautiful ways.